Intermolecular Forces, Chapter 12. The objectives in this chapter: 1. Intermolecular forces or IMFs. 2. Physical properties. 3. Phase calculations. 4. Solids. And 5. Band theory. Your goals. By the end of the chapter, you should be able to identify intermolecular forces in various situations, know the different physical properties and IMF relationships, perform phase change calculations and draw a graphical representation, know crystalline solid properties, understand band theory and their corresponding graphs. 1. Intermolecular forces. We have studied intramolecular forces so far, and these are the bonding forces within one molecule or one particle. These are much stronger than intermolecular forces. Intramolecular forces define the chemical properties of a substance, while intermolecular forces affect the physical properties of a substance. Strong intramolecular forces are bonding forces, such as ionic, covalent, and metallic. They form by either ions interacting, the sharing of electrons, or the sea of electrons, and they have very large energies that are stabilizing, anywhere between 75 kilojoules per mole to 4,000 kilojoules per mole. We saw examples of ionic compounds, covalent compounds, and metallic substances. Intermolecular forces, or IMFs, an attractive interaction that it is electrostatic in nature between two or more atoms, molecules, etc., that hold the particles together in the liquid or the solid state. We oftentimes call these types of interactions non-bonding, and we're going to study all 6 of these in this chapter. Note that these interactions are not as strong as our bonding interactions. Types of IMFs: dispersion. Dispersion is also known as a London force. This is the attractive force between 2 or more particles due to the attraction of temporary dipoles. Well, what causes a temporary dipole? These are caused by fluctuations in electron distribution within particles that result in an instantaneous dipole. The transient or temporary dipole will cause adjacent particles to also polarize and become dipoles themselves. They stick to each other via their partial charges that are temporary. All particles will interact this way, and temporary dipoles can disappear as easily as they form. Let's take a look at a few examples. Xenon is a gas at room temperature, but we can liquefy xenon or solidify it by removing enough energy. In order to do so, though, the xenon particle has to undergo fluctuations of its electron cloud that occur at any given moment, and they're spontaneous and temporary. The fluctuation of the electron cloud will result in a temporary partial positive end and partial negative end. That dipole can now interact with other particles like it via those temporary dipoles. That sticking together between 2 or more particles is called dispersion if it occurs between the temporary dipoles. This can also happen to molecules such as methane. Methane is a gas at room temperature, but it can be liquefied or even solidified. In order to do so, the same type of process occurs. The electron cloud has to be fluctuating. In other words, it's shifting shape and therefore causing a partial positive and a partial negative dipole to form, and it's very temporary. But this temporary dipole can cause temporary dipoles to form on adjacent particles, and then particles can stick to each other via dispersion. Remember that all matter interacts this way. Dispersion force strength. Dispersion force strength will vary. The strength will depend on how easy it is to fluctuate that electron cloud or the polarizability of the particles. The dispersion force strength relates directly to the size of the particle. The larger the electron cloud, hence the atom or the molecule, the easier it is to polarize because outer electrons are held less tightly and are more easily distorted. The larger the particle, the stronger the dispersion forces. For example, consider the boiling points of the following halogens listed from the smallest to the largest. F2, having a small electron cloud, boils at negative 188.1 degrees Celsius. It has very weak intermolecular forces, specifically dispersion force. Chlorine, being a little bit bigger, boils at a higher temperature, negative 34.6 degrees Celsius. Bromine boils at a positive 58.8 degrees Celsius, and iodine boils at a positive 184.4 degrees Celsius. Being the biggest, it has the strongest dispersion forces. The halogens are all nonpolar but differ in boiling points due to the strength of dispersion force. The general periodic trend then, down a group or a family, because atom gets bigger, the stronger the dispersion forces. Dispersion force strength, the number of atoms in a particle. As the number of atoms goes up, the number of IMF opportunities also increases, and therefore the strength of IMF also goes up. For example, consider the boiling points of the following hydrocarbons listed from less to more atoms. Methane, or CH4, boils at negative 164 degrees Celsius. C2H6, a little bit warmer, negative 88.6 degrees Celsius. C4H10, negative 0.5 degrees Celsius. C5H12 at positive 36.1 degrees Celsius. C10H22 boils at a whopping 174.1 degrees Celsius. The key difference? It's going to be the number of atoms. Even though the hydrocarbons are all nonpolar, they differ in boiling points due to the strength of the dispersion forces. The general molecular trend then, the larger the particle, the stronger the dispersion forces are. Dispersion force strength, molecular shape. Long chains have opportunities for interactions that are greater than condensed chains. For example, consider C5H12 and the boiling point of two of the isomers. 2,2-dimethylpropane boils at 9.5 degrees Celsius. This is what it looks like when we look at its condensed structure. And N-pentane boils at 36.1 degrees Celsius, and this is what it looks like when we look at its structure. Even though they both have the same chemical formula, they have different boiling points because the longer the chain, the stronger the dispersion forces. The general molecular trend, compounds with longer chains of atoms have stronger dispersion forces, even if different compounds have the same type and number of atoms. Types of IMFs, dipole-dipole. Dipole-dipole is the attractive force between two or more polar particles due to the attraction of their permanent dipoles. So we have permanent partial positive and partial negative sides. The particles would also have dispersion force, but dipole-dipole will be the dominant IMF because it's made up of permanent dipoles. To determine what IMFs a particle will display, one needs to know overall polarity. That means we have to assign overall polarity. Is the particle polar or nonpolar before we're able to apply the dipole-dipole IMF. Only polar particles have dipole-dipole. Consider the solid state or the liquid state of NF3. It has 26 valence electrons. It has at least one polar bond, the NF bond. The electron geometry and the molecular geometry are not the same. Eg is tetrahedral, Mg is trigonopyramidal, which means it's polar overall. Now that we know it's polar overall, it will also display dipole-dipole along with dispersion. Being that dipole-dipole is the strongest IMF it will display, when we draw that IMF, note that we have to first draw our Lewis dot structure, indicate which end of the structure is partial positive and which one's partial negative. F being the most electronegative will be the partial negative end, and N will be the partial positive end. Now when we have a second particle just like it, the partial negative end of one will interact with the partial positive end of another, and we call that dipole-dipole because it's occurring between the permanent dipoles. Types of IMFs, H bonding. H bonding is a special case of dipole-dipole, but about 10 times stronger. H bonding only occurs between two or more polar molecules if, in each molecule, H is covalently bonded to a very electronegative atom, O, N, or F. It must have that intramolecular force in place. For example, if we consider water in the liquid state or as ice, it has 8 valence electrons, it has at least one polar bond, and H is directly bonded to the O, so that OH bond is extremely polar, and Eg being tetrahedral, Mg being bent, lets us know that overall this particle is going to be very polar. It will have H bonding as well as dispersion, but H bonding will be the dominating IMF. If we take a look at water's Lewis dot structure, drawn to approximate that bent geometry, the O is a partial negative end because it is more electronegative, and the H is a partial positive end, and that's a permanent separation of partial charges. Therefore, when a second water molecule comes into play, the partial positive end of one water molecule will interact with the partial negative end of another. And that interaction there is very strong. It's called hydrogen bonding. It's still an IMF though. H bonding strength. The strength of H bonding arises from the strong difference in electronegativity between hydrogen and F, O, or N. The atoms involved are very small, so other atoms or molecules can get very close to the charge center. And the force strength is equal to a constant times the charge of particle 1 times the charge of particle 2 over the radius squared. The numerator and the denominator help increase the strength of H bonding. What's very special about water is that hydrogen bonding is also responsible for the lower density of the solid, of ice, when we compare it to liquid water. In the solid phase, water will take a strict tetrahedral arrangement, which maximizes hydrogen bonding. In the liquid, water molecules are moving past each other and at times may take less than ideal geometries. Make sure to watch out. Consider formaldehyde as an example, CH2O. Even though formaldehyde contains O and H, they are not bonded to each other. If they're not bonded to each other, a sample of formaldehyde will not display H bonding, but it will have dispersion in dipole-dipole, where dipole-dipole will be the dominating force. So note, you're seeing here the dipole-dipole interaction. There is no H bonding because the O and the H are not directly bonded to each other within one particle. Therefore, if it's polar, it will have dipole-dipole and dispersion. Ion dipole. Ion dipole is the attractive interaction between ions and polar particles. This is a very strong interaction. Ion dipole IMFs are much stronger than dipole-dipole because of the greater charge of the ion. As we saw earlier, the force is proportional to the charges. Consider a solution of salt water or NaCl aqueous. The ions are dissociated in the solvent, that is, they're solvated or surrounded by water. Sodium ion and chloride ion interact with the water primarily via ion dipole. The partial negative end of O interacts with the full positive sodium ion, and the partial positive end of H in water interacts with the full chloride ion's negative charge. Do we expect aqueous calcium bromide to have stronger IMFs than aqueous sodium bromide? Explain. Well, we do expect calcium bromide to have stronger ion dipole interactions because it's a full 2 positive charge with the calcium ion. So it will interact more strongly with water. Ion-induced dipole. This is the attractive interaction that occurs when an ion induces the formation of a dipole in nonpolar particles. Ion-induced dipole is a stronger IMF in dispersion forces since one of the charges is permanent. Consider a mixture of liquid carbon dioxide and sodium chloride. The sodium ion, for example, would cause the polarization of the nonpolar carbon dioxide. Note that normally carbon dioxide is nonpolar, but the electrons get pulled towards the sodium ion. The sodium ion then therefore is inducing a dipole on carbon dioxide, or the name is ion-induced dipole. The chloride ion would cause a similar effect. However, the two substances will not mix well because they differ tremendously in their overall polarities. Dipole-induced dipole. The attractive force that occurs when a polar molecule induces the formation of a dipole in nonpolar particles. Dipole-induced dipole is stronger than dispersion forces since one of the particles is polar. The substances do not mix well. Consider a mixture of water and methane. Water would cause the temporary dipole to form in methane like we see here. We have water with a permanent dipole, and then this would be methane with no permanent dipole. The water forces methane to have a dipole or induces a dipole of methane, which causes a ripple effect and all the particles start sticking to each other. This is a weak interaction, and the mixture will most likely be heterogeneous. 2. Physical properties. IMFs explain the physical properties of matter. In general, the stronger the IMFs that the substance displays, the more difficult it is to disrupt the interactions between the particles. The particles are held together more strongly. By the way, thermal energy also plays a role. The higher the thermal energy, the more disruptions to the interactions between the particles, but we're going to focus more on the IMFs. IMFs affect physical properties such as surface tension, viscosity, and phase changes. Let's consider surface tension. This is the tendency of a liquid to minimize its surface area and results in a very strong inward force. The surface appears to have a skin due to the IMFs that can be broken through with enough energy. For example, surface tension is the reason why some things that are denser than water will float on the surface of water, such as a paper clip that we see here in this image. Molecules at the surface of the liquid interact with each other and with molecules in the liquid, resulting in that inward force. It takes energy to break through that surface, and the IMF relationship is the stronger the IMFs, the stronger the surface tension. Viscosity. Viscosity is a liquid's resistance to flow. A viscous liquid will move less readily. Viscosity is greater with liquids that have stronger IMFs. For examples, the 4 different liquids here in this image have varying viscosities. The first liquid has weaker IMFs, while the last one is more viscous and has the stronger IMFs. Let's do another example. Which is more viscous, water or honey, and why? Well, honey is more viscous than water. It doesn't flow as readily, which means it has to have stronger IMFs. The IMF relationship with viscosity, the stronger the IMFs, the greater the viscosity. Phase changes. Phase changes also depend on IMFs. Let's consider the process of evaporation or vaporization. It is the conversion of a liquid to a gas. It is an endothermic process, which means heat is absorbed for the phase change to occur, and that results in the cooling of the remaining liquid. Why? Well, the temperature is proportional to the kinetic energy. The kinetic energy drops as those molecules with higher kinetic energies escape, so the temperature of the remaining liquid drops too. The IMF relationship. The stronger the IMFs, the lower the rate of evaporation, vaporization. Vapor pressure. Vapor pressure is the pressure of the gas in dynamic equilibrium with its liquid. The phase changes occurs in both directions, to liquid to gas and gas to liquid at the same rate. That's dynamic equilibrium. When liquids are volatile, that means they're easily vaporized and will have high vapor pressures because there will be more particles in the gas state. Liquids that are non-volatile do not easily vaporize and will have low vapor pressures because there's less particles in the gas state. IMF relationship. The stronger the IMFs, the lower the vapor pressure because there are less particles in the gas phase. Boiling point. Boiling point is a temperature at which a liquid's vapor pressure and the atmospheric pressure are the same, or the vapor pressure equals the pressure of the atmosphere. At this temperature, the thermal energy is high enough to cause not just the surface particles like in evaporation, but the interior particles to also become gaseous. The normal boiling point is the boiling point of a liquid at 1 atm or at sea level. For example, we have memorized by now that water boils at 100 degrees Celsius, but that is true at 1 atm. If we had water boiling at different elevations, let's say at the top of Mount Everest where the atmospheric pressure is 0.3 atm, water would boil at 71 degrees Celsius. Let's do an example problem. Which has a higher boiling point and why? Liquid xenon or liquid helium? In both cases, we have nonpolar substances, but xenon is bigger, so it would have greater dispersion forces. So we would expect that greater the force, the higher the boiling point, because it takes more energy to cause the particles to go into the gas state. Though both liquids only display dispersion forces, the dispersion forces in liquid xenon are much stronger than the dispersion forces in liquid helium due to size. Therefore, liquid xenon would have the higher boiling point. Liquid xenon boils at -108 degrees Celsius, while helium in the liquid state will boil at -269 degrees Celsius. The IMF relationship. The stronger the IMFs, the higher the boiling point. Condensation is the conversion of a gas to a liquid. It is an exothermic process. Heat is released for the phase change to occur and results in the warming of the contacted material. For example, steam or water vapor from a hot shower condenses when it hits a cold surface, such as a bathroom mirror. Melting is the conversion of a solid to a liquid. We also call this fusion. Melting is an endothermic process. Heat is absorbed for the phase change to occur and results in the cooling of the surroundings. Consider why ice cools your drink. When ice melts, the solid to liquid phase change requires energy. Energy is absorbed from the surroundings, such as a drink, which then cools the drink. The IMF relationship, the stronger the IMFs, the higher the melting point. Freezing is the opposite. It's the conversion of liquid to solid, and that process is exothermic. Heat is released for the phase change to occur and results in the heating of the surroundings. For example, when a refrigerator makes ice cubes, the refrigerator removes heat to freeze the ice. Sublimation. There are also phase changes that skip the liquid state completely. Sublimation is the conversion of a solid to a gas. The process is endothermic. It takes energy to cause that phase change, and we can see here that iodine can undergo sublimation. It goes directly from the solid to the gas. Deposition is the conversion of a gas to a solid. Process is exothermic. For example, water vapor may deposit itself as ice. Phase change overview. We just noted the phase changes: solid to liquid, which is melting, liquid to gas, which is vaporization. In all of these cases, going from solid all the way to gas, it requires energy. We even saw the skipping of the liquid state through sublimation. Requiring energy means going from a low kinetic energy to high kinetic energy will be endothermic processes. In the opposite direction, the gas can become a liquid via condensation. The liquid can freeze and become a solid, or we can skip the liquid state altogether, go from gas to solid via deposition. In this case, in order to have less kinetic energy, energy is released, or the reverse process is exothermic. 3. Phase calculations. One can calculate how much heat is involved with phase changes and plot the steps of the process. Let's do an example problem together. How much energy is required for a 20.0 gram sample of water at -25.0 degrees Celsius to be heated to 135.0 degrees Celsius? We can use molar heat capacities or specific heat capacities. We can also use enthalpies. In either case, make sure that we're paying attention to units, our starting point, and our ending point. Because we're starting at a temperature below the freezing point of water and ending up at a temperature above the boiling point of water, we have to do this in steps. Step 1. We have to add heat to the ice. The solid ice temperature changes from -25.0 degrees to 0 degrees, its freezing point, or melting point. As heat is added, molecules are vibrating more vigorously but are still in fixed locations in the solid. Because we're changing temperature, we're going to use Q equals mc delta T, where we have to use the C of the ice. The specific heat capacity of ice is not the same as water. It is 2.09 joules per gram degree Celsius. Plugging in our variables, we're going to go ahead and take the mass of water that's given to us, 20.0 grams, times the specific heat capacity of the ice, 2.09 joules per gram degree Celsius, times the change in temperature of the solid, the solid is going to go from negative 25 degrees Celsius to the freezing point or the melting point, 0 degrees Celsius. So 0 minus a negative 25.0 results in a positive 25.0 degrees Celsius delta T. When we put these into our calculator, we should get 1045 joules, and we're going to keep track of our sig figs. We should end up with 3 sig figs, or to the tens place. We're just going to underline it to keep track of it. We have now gotten to the melting point of water. Step 2. Since we're now at the melting point of water, now it has to undergo the phase change. When we have phase changes, the temperature is constant until all of the phase change occurs. In this case, the temperature is constant at 0 degrees Celsius until all of the ice melts. All of the energy added is going to break up the IMFs between the molecules, and the molecules start slipping past each other. During phase changes, the temperature does not change until the entire sample has changed phase. Therefore, we cannot use Q equals mc delta T because delta T is 0. Instead, we're going to use a thermochemical equation. We're going to use the heat of fusion thermochemical equation where H2O solid becomes H2O liquid, and the delta H is equal to positive 6.02 kilojoules per mole. Since we know we have 20.0 grams of water, we can solve for the moles of water that we're going to have undergo the phase change. We're going to end up with 1.11 moles of H2O. For Q2 then, we have to just take the moles of water we just determined times its heat of fusion. When we do so, we're going to end up in units of kilojoules. Since our first heat was in joules, we can convert this one to joules, or we can convert our first heat to kilojoules. Just make sure you have the same unit. Converting Q2 to joules, we end up with 6,683 joules. Keeping track of sig figs, of course. Step 3. Now we're going to heat up the water. The liquid water temperature will now change from 0 degrees Celsius to 100 degrees Celsius. The key points here are the freezing point and the boiling point of the liquid. All the energy absorbed goes to increase the average kinetic energy of the molecules. The molecules move more vigorously, the temperature increases, but the molecules are still stuck together in the liquid phase. So, because we have a temperature difference, we're going to go ahead and use Q equals mc delta T. Since we're working with liquid water, we're going to use the specific heat capacity of water, 4.184 joules per gram degrees Celsius. So Q3 is equal to the mass of water, 20.0 grams, times the specific heat capacity of water, 4.184 joules per gram degrees Celsius, times the change in temperature of the water from its freezing point, that's T initial, to its boiling point, that's T final. That will result in 8,368 joules of energy required. Step 4, vaporization, or phase change. The temperature is going to be held constant at 100 degrees Celsius until all the liquid boils. All of the energy added is going to break all of the IMFs between the molecules. When all the IMFs are broken, the molecules escape into the gas phase. This usually means the temperature remains constant until the entire sample changes phase. If we write our thermochemical equation then, H2O liquid yields H2O gas, we'll have the heat of vaporization. The heat of vaporization for water is 40.7 kilojoules per mole. We know then that Q4 will be equal to the moles of water that we are working with times the heat of vaporization. Taking the moles we calculated earlier, 1.11 moles of water, converting that to kilojoules using our heat of vaporization, and then to joules so we can add them up at the end, we should end up with 45,177 joules of energy required. Step 5. Now we're going to heat the gas. Our target temperature is 135.0 degrees Celsius, so we have to take the water vapor, or the gas, from 100 degrees Celsius to our target. Because the temperature is changing, we're going to go ahead and use Q equals mc delta T. The extra energy added increases the average kinetic energy of the water vapor, the molecules move more vigorously, and the temperature increases. There may also be a detected increase in pressure if the volume is constant. But for Q5, We're going to take the mass of the water, the specific heat capacity of the gas, and then the change in temperature of the gas to determine the heat needed. So Q5 is equal to 20.0 grams of water times 1.84 joules per gram degree Celsius times the temperature change of the gas. We will end up with 1,288 joules of energy required to reach our target temperature. The total energy. The total energy required is the sum of all of the Q's, in this case 5 calculations. Q total then is 6.26 times 10 to the 4th joules. Why did that vaporization process, or Q4, require so much energy relative to the other processes? That's because the dominant IMF that needs to be broken are the H bonds, and that's going to take a lot of energy. Now to plot. To plot the steps, the y-axis is the temperature and the x-axis is the energy added. So here is our y-axis, temperature, and here is our energy added. Key temperatures that we want to make sure to include will be the freezing point and the boiling point. But we started below freezing and we had to heat up our solid, that's Q1. Then at Q2, the temperature stays constant, it's a plateau, because that's the phase change. Then we had to heat up the water, that's Q3, from 0 to 100 degrees Celsius. Then the phase change, Q4, is a plateau, because all of the energy added goes to the phase change and the temperature pretty much stays constant. Once the water has all vaporized, the vapor is heated to the target temperature. Note, a phase change process can also go in reverse. 4. Solids. There are two major types of solids, amorphous and crystalline solids. Amorphous solids have no preferred internal structure, no long-term arrangement or pattern of the particles, such as glass. So this would represent an amorphous atomic molecular level picture. Crystalline solids have an orderly structure or a repetitive pattern of particle arrangement, such as a diamond. The location of where the particles is in the crystal is called the lattice site, a point in a symmetrical pattern of points. This example here shows a repetitive pattern. Atomic crystals. Atomic crystals have atoms at the lattice sites. Atomic crystals are held together by IMFs, specifically dispersion. Properties of atomic solids. Atomic solids are soft, they have low melting points, they are poor conductors of electricity and heat. For example, solid neon is an atomic solid. It is held together by dispersion. Solid neon has a very low melting point of -249 degrees Celsius, and we can imagine each sphere here representing a neon atom held together by weak dispersion forces. Another type of crystal is ionic crystals, and we have seen these before. Ionic crystals have ions at the lattice sites, and the ions cannot freely move. Ionic crystals are held together by strong intramolecular forces, specifically ionic bonds. Properties of ionic solids. They're hard, rigid, and brittle. They have very high melting points. They're poor conductors. For example, solid sodium chloride, or NaCl solid, is an ionic solid. It is held together by strong intramolecular forces, ionic bonds. Solid sodium chloride has a high melting point of 801 degrees Celsius. Molecular crystals have molecules at the lattice sites. Molecular crystals are held together by IMFs. The IMFs involved may vary depending on the polarity of the molecules. Properties of molecular crystals. They're softer than ionic compounds. They have low to moderate melting points because IMFs are holding the particles together. They're poor conductors. For example, nonpolar solid oxygen, or O2 solid, is a molecular crystal being held together only by dispersion forces, so it has a very low melting point of -219 degrees Celsius. Polar solid water, or ice, H2O solid, is a molecular crystal as well, but it's being held together by hydrogen bonding, and it has a melting point of 0 degrees Celsius. Another type of crystal is a covalent network crystal. Covalent network crystals have lattice sites occupied by atoms that are covalently bonded to each other via a strong intramolecular force. The solid crystal is essentially one giant molecule because all of the atoms are covalently bonded to each other. Properties of covalent network crystals: they're very hard, they have very high melting points due to the intramolecular forces, they're non-conductors. For example, diamond, a crystalline type of carbon, is a network covalent crystal and is held together by covalently bonded carbon atoms. It has a very high melting point of about 4,000 degrees Celsius. We also noted metallic crystals. Metallic crystals have lattice positions occupied by metallic cations surrounded by valence electrons or the sea of electrons that are shared by all. Metallic crystals are held together by metallic bonding. These crystals are neutral and are an elemental form of the metal. Properties of metallic crystals: their hardness varies, it depends on the metal. Melting point varies, depends on the metal again. But they're very good conductors of heat and electricity. For example, both sodium metal and iron metal are metallic crystals. The crystals are held together by metallic bonds, but their melting points vary. Sodium has a melting point of 97.8 degrees Celsius, while iron has a melting point of 1535 degrees Celsius. 5. Band theory. Band theory is used to explain the conduction of metals, the semiconduction of metalloids, and the non-conduction of nonmetals. Consider MO theory, where atomic orbitals combine to form molecular orbitals. With a huge number of atoms together, we can separate the MO orbitals into a valence band. These are the bonding MOs. These are the MOs that will contain valence electrons occupied. And then the anti-bonding MOs we can break into the conduction band, and they're empty. In a metal, or a good conductor, the bands are right next to each other, so overlap means electrons can easily move throughout the solid in the conduction band and allows metals to conduct electricity. That's this image here, where the valence band and the conduction band are right next to each other and electrons can freely flow from the valence into the conduction band. In a metalloid or a semiconductor, the bands are close to each other but do not overlap. There is a small band gap. The band gap can be overcome with a little bit of energy, so as temperature goes up, the conduction increases, resulting in the semiconductor properties of metalloids. So in the middle image here, the band gap is small. The valence electrons need a little bit of energy in order to go into the conduction band. In a nonmetal, which is a good insulator relative to the other two, the bands do not overlap and there is a large band gap. A lot of energy is required for the electrons to jump to the conduction band. There's lots of resistance, resulting in the non-conduction properties of nonmetals. So this last image here corresponds to nonmetals where the band gap is large and the valence electrons are not easily able to jump into the conduction band.